Okay, so let's play around with TensorFlow using its lower level APIs so you get more of a appreciation of what's going on under the hood, if you will. On Windows, we'll start by going to our Start menu and finding the Anaconda 3 group. And from there, open up your Anaconda prompt. On Mac or Linux, of course, you'll just open up a terminal prompt and you'll be good. First thing you want to do is make sure that you've actually installed TensorFlow itself. So if you haven't already taken care of that, you can just say conda install TensorFlow. And I've already done that, so it won't actually do anything for me, but if you do need to install that or update it, that will prompt you to do so. Give that a second just to check everything. All right, looks like we're good. Next, you want to cd into the directory where you installed the course materials. So for me, that's going to be cd c:\ml course. And from within the course materials directory, type in Jupyter with a Y, notebook. That should bring up your favorite web browser. Do is import the libraries we need. We're going to be using NumPy and also TensorFlow itself, and the MNIST dataset itself is part of TensorFlow's keras.datasets package, so we can just import that right in and have that data accessible to us. We'll define some convenient variables here. Num classes is 10. That represents the total number of classifications for each one of these images. So again, these can represent the numbers 0 through 9, and that's a total of 10 possible classifications. Our features are 784 in number. And we get that by saying that each image is a 28 by 28 image, right? So we have 28 times 28, which is 784 individual pixels for every training image that we have. So our training features are each individual pixel of every individual image that we're using to train our neural network. Let's start off by loading the data set itself. So we'll say mnist.load data to actually retrieve that data from TensorFlow. And we'll put the resulting data set into these variables here. So the convention that we usually use is that X refers to your feature data. This is your, in our case, the images themselves, and Y refers to your labels. So this will represent whether that image represents the numbers 0 through 9. Furthermore, we split things into training and testing data sets. So with MNIST, we have 60,000 training samples and 10,000 test samples. That means that we're only going to train our neural network using that 60,000 set of training samples, and we're holding aside 10,000 test samples so we can actually test how well our trained network works on data that it's never seen before. This is how we prevent overfitting. We actually evaluate our model based on data that the model has never seen before, so it didn't have a chance to overfit on that data to begin with. Next, we need to convert this to 32-bit floating point values because that's what TensorFlow expects. So we start by creating these NumPy arrays of the underlying training and test data and converting that to np.float32 data types. We then flatten those images down. So it comes in as two-dimensional 28 by 28 images. And there are ways of constructing neural networks that can deal with two-dimensional data. We'll get there. But for now, we're going to keep things simple and just treat each image as a one-dimensional array or vector or tensor, if you will, of 784 features, 784 pixels in this case. The reshape command is what does that. So by saying reshape -1 num features again is 784. That's going to flatten these two-dimensional arrays down to one-dimensional 784 tensors. So that's going to have a new xtrain and a new xtest that contains these 784 pixel one-dimensional tensors. Next, we need to normalize our data. We talked about that in the slides as well. So the raw data coming in from this data set has every pixel represented as an integer value between 0 and 255. 0 represents a black pixel, 255 represents a white pixel, and values in between represent various shades of gray. We need to scale that down to the range of 0 to 1. So to do that very simply, we just divide everything by 255, and we're done. All right, so we've prepared and scrubbed and cleaned our data here. Let's actually do some more stuff with it. Let's start by wrapping our heads around what this data looks like. So it's always a good idea to sort of visualize your data that you're going to be training with and understand its quirks and nuances before you actually try to implement an algorithm. That's what we're doing in this display sample function here. It's going to take as input a specific number of a sample from our training data that we want to look at, and we'll just extract the label of it. So ytrain, again, is a training labels, the numbers 0 through 9 that image represents. And then we'll reshape that back to a two-dimensional 28 by 28 image so we can actually display it on the screen. We'll give it a title. We'll show that two-dimensional image as grayscale and just show it. So let's go ahead and kick that off. Actually, we didn't kick off this previous block yet, did we? So before we forget, go back up to this block where we prepare our data and Shift-Enter to run that. And now that we've done that, we can actually visualize that data that we've loaded. Click down here and Shift Enter. And here's a sample data set point. So sample number 1000 is this image here. And we can see that it's supposed to represent the number 0. And, well, it looks like a 0. So this isn't a particularly challenging one for us to learn, hopefully. You can play around here, try different sample numbers just to get a better feel of what this data is like. So let's try 1500. Turns out that's the number 9. Kind of a weird looking 9, so that might be a little bit of a challenge. Your brain does not do a very good job at all of figuring out what these things represent, right? So every single row of this image represents the input data going into our neural network. So our neural network is going to be able to take every one of those rows of one-dimensional data and try to figure out what number that represents in two-dimensional space. So you can see that it's thinking about the world or perceiving these images more specifically in a very different way than your own brain does. So, it's kind of sometimes a dangerous assumption to think that neural networks work the same way that your brain does. They're inspired by your brain, but they don't always work the same way. So, important distinction there. All right, let's actually start setting up our neural network. So we'll start off by defining some parameters, or hyperparameters, if you will, that define how our training will actually work. The learning rate is basically how quickly we'll descend through gradient descent in trying to find the optimal values, the optimal weights for our neural network. Training steps is basically how many training epochs we'll actually conduct, how many times we'll actually go over and iterate over this entire neural network trying to train it. Batch size is how many random samples we'll take from our training data during each step. And display step is just how often we'll display our progress as we train this neural network. And underscore hidden represents how many hidden neurons we'll have in our hidden layer. So that middle layer of neurons in our neural network will have 512 neurons within it. And you can play with that number, see what number works best for you. These are all hyperparameters, and the dirty little secret of machine learning is that a lot of your success depends on how well you can guess the best values for these. A lot of it's just trial and error, trying to find the right value of the learning rate, the right number of hidden neurons. These numbers are basically determined through experimentation. So, it's not quite the exact science that you might think it is. Let's go ahead and execute that block. Shift Enter. And we're also going to further slice up our data set here and prepare it further for training using TensorFlow. So we're going to use tf.data.dataset to create what's called a dataset object within TensorFlow from our training images and training labels. We will then use that dataset to create our individual batches that we use to train the neural network with. So shuffle 60,000 means I'm going to shuffle all 60,000 training images that I have, just randomly shuffle them all. I will then batch them up into batches of 250 and prefetch the first batch so I have that ready to go. That's all that's going on here. Shift Enter. All right, now we're going to start to actually construct our neural network itself. We'll start by creating the variables that will store the weights and bias terms for each layer of our neural network. So we start off by initializing all of our variables with random variables, just to make sure that we have a set of initial random settings there for our weights. We want to start with something, and for lack of something better, we'll start with random values. Actually, your choice of initialization values can make a big difference in how your neural networks perform, so it's worth looking into how to choose the right initial values for a given type of neural network. We set up our weights here. For the hidden layer, we'll call those weights H, and we'll use our random normal function that we just defined here to initialize those weights randomly. And hidden, as you might recall, again is, let's look up here again, 512. So this will create 512 variables that contain the weights for our hidden neurons. We also need a set of weights on our output layer of 10 output neurons. So the output is going to be 10 neurons, where every neuron represents the likelihood of that being that given classification, 0 through 9. We also need to have biases associated with both of these layers. So B will be the set of biases with our hidden layer. Again, there will be 512 of those. And we also have biases associated with our output layer of 10 neurons at the output layer as well. These will be initialized zeros, okay? So a little bit different there for the biases. By default, we want our biases to be 0. Let's go ahead and execute that. All right, moving on.